According to start, yeah. Tell me, Tashu, what do you want to say? Yeah, Tashu, you want to say something?
Ma'am, I was asking when will the college reopen for the first years? Because yesterday Manish, so they also said no something.
Abhi, nothing has been decided, and no notification from the university so far. Once it is known to us, once uh, there is a notification from the university, we will let you know, beta. Okay, right?
Okay, ma'am. Thank you, ma'am.
You can keep on
Okay, ma'am.
checking the college website as well as the university website. So whatever new notifications come in, they are instantly loaded on the website. Okay, just give me a second, please. Okay, in the last class, students, we discussed the instruction cycle. We saw that each instruction needs to go through 4 phases. Can you name them for me?
Fetching phase, decode phase,
Yes.
then to find effective address and to
And finally, the
execute the instruction.
Execution of instruction.
right. What do we do in the fetch phase?
First, we set sequence counter to 0 and then fetch instruction from the main memory and then transfer it to instruction register.
And increase program counter
Right. We
is 1.
fetch the instruction from the, yes, we fetch the instruction from the main memory into the program counter by first transferring the contents of the program counter into the
Address register.
right. Okay. Then we transfer the contents of the memory into the
Instruction register.
good. And finally, we increment PC,
Program
right?
counter.
So that it starts pointing to the next instruction. Then comes the decode phase, right? Then comes the decode phase. Now, in the decode phase, what do? We simply copy the mode bit into a flip-flop. We call it I. We name the flip-flop I because it symbolizes the indirect bit. We apply the 3 bits, that is bit number 12, 13 and 14 to a 3x8 decoder that lets us decode which out of the 8 options given to us at that time can be chosen. Okay, so it chooses an opcode between D0 to D7. We had already pre-decided as per the basic computer that opcodes D0 to D6 will belong to memory reference instructions and D7 will be shared by
Register reference instruction.
and
Input output.
very good, right? Yeah. So making use of these 4 bits, right? Bit number 12 to bit number 15, the control unit deciphers, it decodes what operation is to be performed. The remaining bits give us the operand either directly or indirectly. Yes? Is there any problem? Is there any problem in any of this?
No, ma'am.
No, ma'am.
Okay, right. So today I'm going to show you how do we use CPUSim, okay, to first of all, we will make a fetch sequence, and then I'll show you how to execute a simple register reference instruction. We'll take, let's say, CLA, which is one of the very simplest instructions. Okay, so the goal today is to familiarize ourselves with CPUSim, how to make a fetch sequence. Fetch sequence is going to be very important, as you can imagine, for execution of any of the instructions. It involves here the fetch sequence that we are going to see, we're going to make today in CPUSim will actually encompass both the phases, the fetch phase and the decode phase as well. Okay, so first we will see how to make the fetch sequence, and then we will actually execute the fetch sequence to fetch another instruction, let's say CLA, okay, and execute that instruction also. Okay, so this is the uh, task that I have set for today. Okay, now this machine that you see that opens by default when CPUSim is opened is Wombat 1. As I told you in the last class that I took on CPUSim, if you remember. This is a sample machine given to us for our reference. I'm going to just close this. Going to open a new machine now. I've named it demo.cpu. Okay. If you remember, all machines must be saved with the extension. What is the extension of the machines that we make?
Ma'am, CPU extension.
It is
Dot CP.
CPU.
.cpu. Okay, right. So I had given you a task to do. I hope all of you are ready with it on your machines. If not, please complete that today so that you can do the exercises that I'm going to do with you today. Okay, so exactly in the same format, I have this machine ready with us. So this machine is a new machine now, okay, with only the registers and the main memory created, as I demonstrated to you in the last class when we discussed CPUSim. Okay, right. So the first thing that we're going to do is to make the fetch sequence. Now there'll be a set of concepts, new things that you will see today when I discuss the fetch sequence with you. So within this context itself, I will uh, discuss those things with you. So I request your attention, please. So how to create the fetch sequence? We go to modify hardware modules, right? And from here, fetch sequence, right? Now, please see, what is the first thing that we must do to implement the fetch sequence? What was the first step?
Sequence counter to 0.
Apart from setting the sequence counter is equal to 0, the first actual step is to transfer the contents of the program counter to the address register. Am I right?
Yes, ma'am.
Yes,
Yes.
ma'am.
Okay. So now, so the first micro instruction that I must made that I must make is to transfer the contents from one register to another, that is from PC to AR, right? Okay.
Yes, ma'am.
Yes, ma'am.
Please see here in this dialog box, right hand side, you can see the type of micro instructions listed. Okay. The first one is transfer R to R, means transfer from one register to another. Next one, transfer from an address in the memory to the register. Transfer the contents of a register to an address in the memory is next. Then is set. That means if we need to set the value of any register. Then test. I'll be talking about test later. Today we will also be using increment. Okay. When we talk about incrementing the program counter, then there are several arithmetic micro operations. For example, add, subtract, etc. Right? Shift. I will be demonstrating to you. First, I'll be explaining the concept of shift micro instructions to you in the class, and then I'll show you how to implement here. So, all in all, you see a lot of micro instructions, listed here. What we must do first is we need to identify what category out of these will the micro instruction that I want to build belong to. Okay, that means I need to understand, I need to identify if I want to make this micro instruction PC goes to AR, in which category would this instruction belong to? Okay, so it will belong to which category? Can you see that?
Transfer R to R.
Yes, ma'am.
Very good. So I say transfer R to R. Now, as soon as I double click on this, you see another dialog box opening before you, in which we can make our new micro instruction. Okay, so you can see this type of micro instruction R2R written here, and I can just press this push button. Okay, and I can make a new instruction. Okay, let us see what are the parameters that I need to supply to make this new micro instruction. Okay, first of all, I need to give this a name. So I'm sounding a caution here. Please don't name the instructions X, Y, Z, A, B, C, A1, A2, A3. Okay. Please give meaningful names, very meaningful names, because later you will have to find out these micro instructions that you are now building to build up machine instructions. Okay. I'll come to this again in a while. So I am naming this as PC to AR. Okay. Akin to the task that I have on hand, I choose my name very carefully, right? Then I need to choose the source register. Okay. So what is the source register here?
PC.
PC. These are the registers, mind you, These are the registers that we had made last time, and they are now visible to me in this drop down. Okay, so PC. Then I need to specify the start bit of the source register, in our case PC, from where I want to start the data transfer. Okay, so since we want to transfer the entire contents of PC to AR, therefore I'm giving the start bit as 0 only. Okay, we can also, this obviously gives you an idea that you can also partially transfer the contents of a register to another register, which is sometimes done. Okay, which is sometimes done. For instance, if we have the destination register as a 8-bit register, but my source register is a 16-bit register. So you may have to choose whether you want to transfer the lower byte or the higher byte of the register. Lower byte means the bits from 0 to 8. Higher byte means 9 to 16, 9 to 15. Okay, is this clear? Right?
Yes,
So
ma'am.
sometimes this kind of a transfer is required. So that is why an option here to select the start bit, right? What is the destination register in our case?
AR.
AR. And the destination start bit? 0. Again, the same logic here. Why ask the bit from where to start the transfer? Again, the same bit if it were the reverse. For instance, if I were to uh, transfer the contents of input register, let's say in AC, right? You know that the contents of the input register are directly transferred to AC and from AC to output register, right? So, and you know that as per the basic computer, the input register is only input and output registers both are 8-bit long, and the AC is 16 bits long, right? So this gives us a finer control over the transfer operation, right? After this, we need to specify how many bits are required to be transferred. How many bits should I put here?
12.
Yes, 12. We will put in 12. Okay. Please see if I try and put in 16 bits here, what happens? Let me say okay. What does this say? The bitwise width of the transfer area is too large to fit in either the source or the destination registers. Why? Because the registers, address registers, both of them are address registers, right? And we made them to be 12-bit long only. How can it fit a 16-bit data in 12-bit registers? Is this clear to everybody?
Yes,
What
ma'am.
we have done
Yes,
so far,
ma'am.
right? So I'll simply say okay, right? And now you can see your micro instruction appearing under the label transfer R2R, right? Okay.
Yes, ma'am.
I insert this in my fetch sequence. Okay, I select this and I insert this in my implementation. Is this clear so far?
Yes,
Right?
ma'am.
What is the next thing that we must do? We need to go to the memory, add the address pointed to by address register, and get those contents in the instruction register, right? In other words, do I need to do a memory read now? I need to read from the memory. Yes or no? Are you there, students?
Yes, ma'am.
क्या परेशानी है बेटा? What is there to not understand here? Please see. What do I want to do next? I want to go to the memory and I want to read the contents from there, which are located at the address pointed to by AR, right? This
Yes,
will be
ma'am.
known as the memory read operation. Okay. Now, to create a micro instruction for this, please see there is a label called memory access out here. Okay. Now, I double click on this. I say new and let this be the name. This is what you want to do, right? So accordingly, I have given the name, right? This is just a name, by the way, could be anything. But as I told you, please choose meaningful names. Now, what is the direction of memory access? Do you want to read from the memory or do you want to write something into the memory?
Read.
You want to read, right? What is the name of my memory? There is a single memory that I've created so far and I've named it main, right? And then where do you want the data to go? I want to go in
IR.
the register, right? And where would the address be? It will be in the
AR.
address register. Okay. Any problem?
No, ma'am.
Let's say okay. Now let's insert this as well to my implementation. Okay. Now when I inserted it, please see it comes above the earlier instruction, but you can modify the sequence from here by dragging them up and down. Okay. After this, what do we need to do? We need to increment the PC. So I'll go to the increment label, double click, say new. Let's call it increment AC. Which register is to be incremented? AC. What is the halt bit? I'll let you know, but you need to set this halt bit in case there is an overflow. Okay, I'll explain this later to you. Today the focus is on the basics. Okay, so let us stick to this. Halt bit is not a bit that I have created. Okay, halt bit is set internally. It is already there in all new machines. The basic purpose is that if there is a overflow, okay, when we are incrementing anything, that means we are adding something to the existing contents of the of a particular register, there is always a scope for overflow, right? So halt bit, setting the halt bit amounts to halting your program. Okay, so what we're doing here is that I'm saying that in case there is an overflow, please do not proceed, just halt. Okay, this is required to be done. Okay, now delta
Ma'am,
is
excuse
the
me.
amount.
Excuse me, ma'am.
Ma'am,
Yes,
program counter should be increased, not AC.
yes. I was just waiting to see if somebody is, actually not sleeping. Had lunch, everybody. Yes. And then
Yes.
did what? Want to sleep now?
No,
Okay,
ma'am.
right. So you told this a bit earlier, otherwise I would have implemented and then asked you to go back and find out the fault. Why is it not working? Okay, चलो देखो अभी. So by what quantum do I want to increment? I want to increment it by 1. Okay, so the amount by which you want to increment, you can give that here. Okay, so I say this, let's say okay, and let's transfer this to our fetch sequence. Let me bring this down here. Okay, now the fetch phase, as you can see, is complete now. The fetch phase is complete. However, we also need to decode the instructions. So the fetch sequence in the CPUSim machine also involves decoding. So this is a combination of both the fetch and the decode phase. Okay. So how to decode? There is a provision here. You don't need to do much actually. Just go here and double click here. We'll say new as usual. Okay. Let's name the instruction as decode. Which register do I want to decode? Which register do we want to decode, children?
Instruction register.
So I have chosen IR from here, and that is all we need to do. Okay, that is all we need to do. Rest will be handled by the hardware. Okay, so I'll say okay. Okay, and now let us transfer this statement as well to our fetch sequence. Put it in sequence, and we will say okay. Okay, so my fetch sequence is now ready. Is this clear to everybody? Any problem up till now?
No, ma'am.
No, ma'am.
Okay, good.
Okay, ma'am.
Yes.
Ma'am, I was doing this side by side, but
No,
what's
no, no,
happening
no,
is,
no, 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 no. Please don't do it side by side. Okay. See, I can explain this to you in flat 5 minutes and move on. Why am I giving it so much time? Why do I speak so slowly? Explain again. There is a reason. Okay. Even if you were in the class, I would have told you to, when I teach you, you need to put your pens down, okay, and just listen. Okay. Please don't mix implementation, especially if you're doing it for the first time, with the understanding part. Okay, these are two different phases initially. Right? Okay.
okay, ma'am.
Uh, प्लीज डू इट लेटर अगेन फ्रॉम स्क्रैच. आप छोटी सी गलती करोगे ना बेटा, आपको कम से कम 10 एरर आएंगे इसमें, और आप यू विल नॉट बी एबल टू फाइंड आउट वेयर यू हैव अर्ड. इज दिस क्लियर? राइट?
Yes, ma'am.
Yeah. So you need to see all the settings very carefully. You will have my recording with you later. You can do the same thing later, but अभी आप समझ लीजिए. Clear? The second thing is that I don't want to shift the focus of the entire class in debugging one child's, error. Okay. So I will not take your query right now. Let that be. We can look at it later. Is that okay? Right?
Okay, ma'am.
Okay. Is this clear to everybody? This is something that you don't do in any other programming language. This is not something that you've seen so far. This is very new for you. The interface is new for you. Everything about CPUSim is very new to you. Okay. So that is why I need you to focus, right? So this is the fetch sequence first of all. Okay. Now we are going to, first of all, build up a new instruction. As we had decided, let's say CLA, okay, and then we will execute it. Now, before I go there, I'll change my screen. I'm going to take you to the presentation that we were looking at yesterday. and then we'll come back here. Let me know when the screen is visible to you.
It's visible, ma'am.
Right. Thank you. Please see here. So this is a table wherein the register reference instructions along with their execution are listed. Okay. So the first instruction in this sequence you see is CLA, stands for clear accumulator. Okay. Clear AC, right? Now, please see from our discussion, we already know that any register reference instruction will be executed when D7 will be 1, right?
Yes, ma'am.
Yes, ma'am.
And I will be
0.
I will be 0,
0.
right? Okay. And all register reference instructions took place in this time signal T3, right? Okay. So when D7 was 1, I was 0 and T3 time signal is active, right? Now, so what are we doing? We are, so that we don't have to write this again and again, we simply, you know, put this together as R, and then they are saying R here. Okay, what they're saying R here. R means that when the CLA will be executed, what is the meaning of this micro instruction that you see before you? The meaning of this micro instruction is that only when D7 is 1, I is 0 and T3 time signal is active, and so this is R, and B11 is 1, bit 11 is 1. So if this is my instruction register, if this is the instruction register, what is the meaning of D7I dash? Although please see that so far in our discussions, we have always looked at the I bit as the 15th bit, but it doesn't really make any difference. In the execution now, what they've done is they have changed the position of I after D7. So equivalently, what they mean to say is that bits 13, 14, 15 will specify the opcode, and the 12th bit will now specify I, but all other things remain the same. Okay, is this clear?
Yes,
Right?
ma'am.
And that does not actually make any difference, right? So please see, this statement says that when R is active, R means D7, D7 means 111 here, I dash means 0 here in the 12th bit, right? Any problem so far?
No, ma'am.
This is the 16-bit instruction register that you can see here. So 4 bits, 4 bits, 4 bits, then the last 4 bits. So bit number 12, 13, 14, 15. This is D7. This is I dash. Okay. So for all these register reference instructions, you will see their opcode will always start with E. What is E? E is 1110. 1110, which is 14. Okay, is this clear to everybody?
Yes, ma'am.
Right? Yeah. After that, please see they're saying R. This is R, right? B11. B11 is 1. So bit number 11 is 1. What is bit number 11? This is the bit number 11. Isn't it? Yes or no?
Yes, ma'am.
So this is 1. Okay. So if I look at this and change this into hex now, what do I get? I get E 8, this is 8, 0, 0. Am I right?
Yes, ma'am.
Yes, ma'am.
Is this clear to everybody?
Yes, ma'am.
Yes, ma'am.
Very good. Okay, so we will remember this. Let us go back to CPUSim now. Okay, yeah. So now let us see how to make a new micro instruction. Actually, CLA is called a machine instruction, although it is very small that it only encompasses a single micro instruction. But later you will see machine instructions which contain more than one micro instruction. Okay, so a micro operation is an operation which is a very basic atomic operation which cannot be divided any further, is generally done at the level of the registers. Okay, so transfer from one register to another, complement of a register, these are all atomic operations. Any instruction that specifies these operations is called a micro instruction. This is all that we have done earlier, so I'm just repeating it. And a set of micro instructions together forms what do we call a machine instruction. Okay, so let us make CLA now. Okay, I go to modify and I say machine instruction. Okay, let me just delete this first. So there are no machine instructions now. Okay, so let me say new. Let me type the name here, CLA. Let us keep it CLA. Okay. And what is the opcode that we had decided? E800.
00.
Okay. So we will keep the same opcodes here because of two reasons. The first one is that we want to see and execute the instructions as they are given in our book. Okay. The second is that our practical guidelines also tell us to these opcodes are also listed as it is there, that please make machine instruction this with this opcode. Okay, now this is clear, right? Up till here it is clear, I think. No problem. Is there any problem so far?
No, ma'am.
Right. Now what should I write in the format? Okay, what should I write in the format? So what is the meaning of format? Format means that how will this instruction appear in the let's say assembly language program or machine language program where I will be using it. How will this instruction appear there? So for the time being, we can say that only this opcode is required. No other address is required. Nothing is required. Yes. Nothing else is required. So I'll simply go from edit fields here. I have added a new field. Okay, let us delete this. I'm adding this here. Okay, known as, let's call it opcode. Okay, We will set it to be required, because without giving an opcode, obviously, we cannot. You have to at least write down CLA. Okay, CLA has the opcode this. So without giving the opcode, no instruction will be executed, right? So we will say required, yes. How many number of bits have we used here? How many number of bits were there in the presentation we saw?
16.
16.
Right? Okay. And for the time being, please let us leave the remaining things as it is. Just set sign to off. Okay, that's it. These are the things that you need to remember for the time being. Is this clear? Right? Then we
Yes.
say okay. Clear? And here in the format now, I'll simply say opcode. That whenever I want to use this instruction CLA, I will be mentioning only the opcode. Okay, that means I will just say CLA, okay, and that should do the job. Okay, clear?
Yes, ma'am.
Right. Let me show this to you again in case you want to. Uh, please see, to create the CLA micro instruction, machine instruction, I simply go to modify, say machine instruction, and then I say new. In the edit fields, first of all, I have typed this opcode, required number of bits 16, and I've said okay. Okay. And now, and now I say new, and then I say CLA opcode is E800, and in the format I just want to say opcode. Is this clear? Right? And this is it. Now, here we need to specify that once I have written this, what is the series of micro instructions that should be executed? That means once in my program, this instruction with the name CLA is encountered, what micro instructions should be executed? Okay. So what should be done? Only AC should be cleared to 0. Okay. Or can I say AC should be set to 0, right? Is
Yes,
that
ma'am.
right?
Yes, ma'am.
Students?
Yes, ma'am.
Okay. So how to do that? I will create there is no micro instruction under the set label right now. So I'll create a new instruction here, right? Saying set AC to 0. Okay. So which register do I want to perform this operation on? AC. What is the starting? Where do I want to start from? From 0th bit. How many bits do I want to set? All the
One.
bits. So I set, say 16. What is the value I want to set to? 0. Is this clear?
Yes.
Yes,
Anything that
ma'am.
is not clear here in this dialog box? And then I say okay, right? And then I transfer this here. Okay. Now after this, please see, I need to say end. Now please see, end is not a micro that we have created. It is already present. Okay. So what will this do? This will end this. This simply tells the CPUSim that there are no more micro instructions to be executed when CLA is executed. Okay, this is the only thing that we need to do, right?
Yes, ma'am.
Okay, so we say okay. In fact, we should have put an end in the fetch sequence as well. So I'm going back to the fetch sequence and putting a end statement here as well. Okay, is this clear?
Yes, ma'am.
Okay.
Yes, ma'am.
Yes, ma'am.
Now let us open a new text window and just type CLA here. You can see that as soon as I type CLA, it turns blue, indicating that this is a kind of a keyword. Okay, you know what are keywords or reserved words in C, C++, right?
Yes, ma'am.
Yes, ma'am.
Instructions which are recognized. Suppose I turn it to CLS. Please see, we have not made any instruction with the name CLS, so it doesn't recognize it. It stays the same way. But as soon as I say CLA, there's a spark here, okay, to suggest that, oh yeah, I recognize that this is a valid instruction that is available with me and I can execute it. Okay, is this clear? Okay. So what do I want to do now? I simply want to perform CLA. So I've simply written CLA here. Okay. Let me just save this. So this is what this is. I'm sorry. This is a simple program that I have created. I'm trying to create here assembly language program with only one instruction CLA. Okay, and I will now execute it. Okay. Now the machines, that is the complete files that we create using CPUSim, are saved with the extension .cpu, and the assembly language programs that we create, they are saved with the extension .a. Okay, so let me save this as demo, which is the name of my machine, and CLA. Okay, .a. Is this clear? Okay, this is just a name, by the way, but is this clear? Now let us execute it. Now before we execute this, let us look at this menu, execute. Please see there are a variety of options here. Okay, the first is assemble. What do we mean by assemble? Whenever we say assemble, then this assembly language program is changed into its equivalent binary code. Okay, the conversion of the assembly language program to the corresponding machine language program, that is binary code, is known as assembly. Okay, so that is done. Obviously, as I've told you many times, that is the first step towards execution of any program. Now what happens is when you do this in C, C++, you don't see this happening. You don't do it with your own hand. I think you just press Control F9. What do? I don't, we used to use a DOS based terminal. So we used to do Control F9, I think.
Yes.
I don't know what
Yes,
you
ma'am.
do.
Yes,
So
ma'am.
yeah. So I don't know what you are using these days and what is the combination, but whatever. So you press a key combination and that does compiling as well as execution for you. Okay, so there are two steps that are being done. So compilation is conversion from, I think Archana ma'am must have told you about this. Do you know what is compilation? Please don't sit quietly, bache. You always have the option of saying no.
Ma'am, it's convert high-level language into the binary language so that the computer understand.
Very good, very good. So conversion of a high-level program into its equivalent binary program is known as, it is known as
Compilation.
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 And What is assembly? Conversion of the assembly language program into the corresponding binary level program. Okay. So actually, is it too much for you? Are you feeling saturated? Should I stop
Yes,
for
ma'am.
today?
Yes, ma'am.
Okay. Okay, I'll do this, but you have to promise me that you will practice all this yourself so that next time I can, from this step onwards. Okay? Right?
Okay, ma'am.
Okay,
Okay,
ma'am.
ma'am. Ma'am,
Ma'am,
please
excuse
upload
me.
recording on classroom.
Sorry, come again.
Ma'am, excuse me.
Come again, beta.
Ma'am, please upload a recording on classroom.
I will. I will. Okay.
Ma'am, excuse me.
Yes, tell me.
मैम मैंने आपने बोला था कि वॉम्बेट डाल के देख लेना